Hello everyone, this is Group 11 consisting of Shreya, Kunal and Alan. This is a computational geometry project. So the basic problem asks what is the minimum number of stationary guards needed to see every point inside the polygon art gallery. For our project, we have implemented an important extra real-life feature, solving the problem for polygons that contain internal holes, which represent obstacle or courtyard in real-life scenarios that a guard cannot see through. We have made this project in Python using Kinter GUI and Matplotlib for visualization. So let's start. We have done modular coding, so you can see each file has its own use case. So I will start with main.py. This file is the brain of our project. It creates a GUI that allows user to input field and step-by-step buttons. It manages program state, storing the polygon, holes, triangle and guards. And it also combine all the calling functions from other files and modules. Now we have polygon generator. So this is the architect of our module. Its job is to design the art gallery. It first generates a random simple polygon for the outer boundary. Then it uses robust technique to add holes. It performs a temporary triangulation on the outer polygon to find large guaranteed safe holes and then generate new randomly shaped holes entirely within these zones. This ensures that zones are correctly inside and does not overlap with the boundary of the polygon and doesn't intersect with each other. Now we have triangulation.py. This is the most complex and critical part of our project. Its main goal is to take polygon with holes and convert it into set of simple triangles. It does this thing using a merge and clip strategy. First it finds the shortest valid non-intersecting bridge to connect each hole to the main boundary. This merge operation transforms the complex shape into a single large simple polygon. Secondly, triangulates this new polygon into the robust ear clipping algorithm. Now we have art gallery pie. So once the gallery is divided into triangles, this module acts as a strategist to find to where to actually place the guard. We use set cover algorithm, which is the correct method actually to place guards for polygon with holes. It works by greedily picking the vertex that covers the most uncovered triangles at each step until the entire gallery is visible. This is more robust than the simple three coloring method that we used to do in case when we do not have any holes. Now we have the plotting.py. This is the UI. It handles all the visualizations and contains the function to draw everything you see on the screen. We have added some extra feature like red holes or dashed line to represent boundaries and many more features for users accessibility. Now we have geometry.utils. It contains mostly the edge cases that it doesn't intersect or doesn't overlap, and also contains the primitive geometric functions and calculations that are needed. So now let's start with our demo. So I will run this main file. As you can see, we have input of number of polygon. For example, we take n is equal to 8. Number of holes, for initially we take 0 holes words. So as you can see, we got a 8 size polygon. We have done trapezoidize of this polygon. Then we triangulate this polygon. As we can see, the dual graph, and we can see only one vertex is needed, vertex guard is needed to cover this whole polygon. Similarly, we can do for some 10 polygon, 0 size, trapezoids, triangulate, show dual graph, solve art gallery problem. Here we need two vertex guards. So now we will take some holes. For example, we take 3 holes, 10, max hole vertex, let's say 4, generate a polygon. So we can see 10 size vertex, polygon with 3 holes. So we generate a, sorry, I clicked it by mistake. We generated a polygon. Now, as this is our, we have implemented a new algorithm without, with having holes. So it doesn't do trapezoids. It do merge with the bridge. So in this case, it merges the hole with the external boundary of the polygon. That will ensure this whole polygon is only a single part, and this is the part of external boundary. So as you can see, now we triangulate this region, and we can see we have gotten 5 guards. You can see all places are covered by each guards. For example, if we take, for example, 17, number of folds 2 for better visibility. You can see this. We can take this. So we do merge with bridges. So you can see it is merged with the bridges. So now we have only one polygon, and this is merged with the external boundary. So we have one polygon. Now we do the triangulation, and you can see we have got the 7 guards are required. We have compiled the result here, and you can also confirm with n plus 2h upon 3. It is always less than or equal to the number of minimum guards required to cover the whole polygon with holes. For example, now we take the case of 22, maximum number of holes. For example, we take 4, we take 5, we generated a polygon. So you see we merged it with the external boundaries. Now we triangulated every region, and we place the guards. In this case, we have to keep in mind we are not using the usual dual graph or the trapezoid. We are using another method called set cover algorithm that basically readily chooses the unselected triangles from this, and it makes sure every spot in this polygon with holes is covered. So it is not our usual 3 coloring graph, as it has holes, so it won't be working correctly. So we have optimized this approach. For example, if we take one generate polygon, you can see here merge with bridge, it is merged. Then we triangulate all the regions available, then we put, so in just 6 guards we are able to, as you can see, this point is also covered by this point is also covered by this area is covering everything. So by doing this, we are able to fully navigate the polygon with holes. So this was a robust merging strategy that finds the shortest valid to valid vertex to vertex bridge, as you can see here. If we take one more example, like I will show you 23 0 holes. So see, we do a trapezoidalization, then we triangulate it, show the dual graph, and you can see guards 5. It is, as we know, it is less than n upon 3, that is 8 here in this case. We are able to manage with 5 vertex. So our application successfully demonstrates a complete step-by-step solution to ArtGallery problem with holes, from geometric construction to final guard placement. Thank you for watching.